Today, I'm joined by Dr. Yasunori Nomura, professor in the UC Berkeley Physics Department. He's widely known for his work on quantum gravity and black holes, especially for addressing how information is preserved in black holes and for developing rigorous quantum frameworks for space-time horizons and the multiverse. Professor, welcome to the show.
Thank you very much. Thank you for the invitation.
Yeah, thanks for joining us. So, one of your colleagues, John Clark, recently received Nobel Prize.
We are pretty happy, by the way.
You're happy?
Yeah.
Do you get to talk to him sometimes?
Yeah. He's still active and then coming around. He's emeritus already.
Oh, okay.
But he's coming to like faculty meeting and a lot of events and so on. Yeah, we talk reasonably often, like every month or something like that.
Right.
But not after, of course, the announcement.
Oh,
he's
really?
so busy.
He's so busy.
He must be so busy. And
Did you guys like get together and celebrate? How what's the perception?
Oh yeah, I think we celebrated on the department as well.
Right.
Of course, university-wide, there was some press conference and so on. But the department had some small celebration event. But I was in Japan at that time.
Oh, you missed the party. The party.
Of course, I sent some message and so on, but I missed that party.
Okay. Yeah. Were you kind of like working on something similar with them, or did you ever collaborate with them?
Yeah, not really the collaboration. The first of all, in physics, the scientists who were doing theoretical work and experimental work are kind of different.
That's right.
Yeah.
You're on the experiment side.
No, I'm on the theory side.
You're the theory side.
And he's an experimentalist.
Okay.
So collaboration is, but even a theorist and experimentalist sometimes collaborate. But when I was in like a professor and so on, he was already fairly old and then retired. And my initial field was something called particle physics,
right?
Like analyzing the building block of nature.
Yes.
And he's doing some called condensed matter physics,
right?
Like superconductor and so on material. So it's not really truly overlapping.
Is it like rare for experimental side to receive Nobel Prize, or what's the ratio? Like
I think it's
recognized?
Like 40%, like 70-30 or something like that. But actually, the number of people who do an experiment is much bigger than the theory.
I see. I thought they would get paired up to receive the Nobel Prize because it takes two to sort of tango, so to speak. Right?
Not necessarily, depending on the progress. For example, somebody proposed some theoretical framework, and some experimentalists checked that, and that was a big thing. And these two happened around the same time. Then quite often, yes, Nobel combined these two. But sometimes, like some theoretical work is like 40 years ago, an experiment was developed later, and so on, and not necessarily pair up.
I see.
So,
okay. Speaking of Nobel Prize, Dr. Jeffrey Hinton. I don't know. He doesn't work at the UC Berkeley. He's with Princeton or something.
Not.
What do you make of the fact that he's sort of like he's a neuroscientist and then basically an engineer, so to speak, who built AI, to be able to receive Nobel Prize in physics. Was that a surprise to you?
Not completely. Yeah, it's to some extent, in a sense that it's in terms of the field of physics, it's not really truly conventional physics, but physics evolves. And and for example, like technology, the physics prizes are often awarded to technology people, right?
Really?
Blue LED and so on.
Right.
Yeah, of course, even LSI, like Jack Kilby in, I think it's where IBM, no. But those things are quite common because that will, the progress in society, that's one of the Nobel's will, that this prize should be awarded for the people who contributed to humans, advancement. And in that sense, it's quite normal, and the AI, of course, it's a big deal, and it is timely. And Nobel Committee also cares to some extent timeliness, right? For example, messenger RNA vaccination got the Nobel Prize after COVID and so on. AI now getting the prize is not super surprising in that sense.
Okay, what if AI one day came out with something, some sort of like, what if AI did something like a breakthrough, so to speak, what happens to then? Like who gets the Nobel Prize? I mean, AI is like actually a machine.
Yeah.
It's not human.
Yeah. If it's AI really like pose a question
Right.
and then solve it and so on, then it will be difficult. But at this point, it's far away. I think AI is pretty useful for research. For example, we can even have a conversation with the AI to develop the idea, like back and forth, and so on. And the AI can do the search of literature and can even summarize like, tons of literature in a compact way and so on. It's very helpful. But in that sense, it's not that different when computer first came out, right? The computer, people are doing some integral, very difficult integral. Those kind of scientists were great. I mean, that guy can do a very difficult integral nobody can do. Now, of course, you just type in. But that didn't replace scientists. Computer is useful. People using computer. If you can't use it, you are disadvantageous. The AI, the similar thing will happen. If it's more than that, like something helping like human researchers is not clear. So I cannot imagine, to be honest, at this point that happens.
Okay, some argue that in 2 years it'll be AGI, and then right next to that would be ASI, like artificial superintelligence, like singularity is very near. I don't know. There's so many arguments these days.
Yeah, of course. To me, I don't know. That's the honest answer. But just the feeling from just my daily research and so on. I'm also using AI, but it's not real AI. It's at the level of LLM.
Right.
LLM is not necessarily AI, right? It's just simply like conversational tool. And at that level, I don't see it yet. So it would be surprising if, for example, human scientists are completely replaced in next 2 years. It would be surprising. And who knows? I mean, it may happen. Some people say it will happen, but to me, I don't feel that it's very likely at least.
So LLM will never become sentient. I actually have the same idea in that subject actually, but I believe that us humans are basically any life form basically has to be set on a game theoretical platform. So you have to have a game. You have to have pain points basically to be sentient. AI doesn't have a pain point. You can't hurt him, right? So that's the key. I think that's something that many scientists and engineers are working on, I guess. But some argue, it's gonna be in 2 years.
Those kind of like a physical nature, like AI may get it. For example, like a sensor, right? We have sensor technology and so on, and those things maybe, and also like AI is now it's like robotics combined with the robotics.
Yes.
And moving around and so on, doing things. Those things will develop for sure.
Yeah.
But the point is whether it can replace human scientists or something, because we're talking scientists. Yes, and then pose a question himself.
Right.
And what's the right question? What's the things human are interested? And then so that's a bit far.
Yeah.
But 5 years later, I have no idea. But 1 or 2 years, I kind of doubt.
Right.
But,
if they don't have pain points, it's very difficult for them they don't have any game actually. If there's no game, there's no life. And if there's no life, there's no consciousness. So I truly believe that we're on the same page. I think.
Somehow the consciousness. I mean, defining consciousness is so hard. I mean, for example, you can define a consciousness. I mean, dog's consciousness, because for sure they have some sort of emotion. And then what about the insect? Whatever. What about the AI? So the definition will be difficult, but just a narrow question, like this is a very big question. It's interesting, but so far I'm so useless to answer that. So if it's a narrow defined question of whether they can completely replace human researchers or not, in the next 1 or 2 years, I'm doubtful. That's my feeling.
Yes, and let's go back to your field actually. So you're in quantum physics and string theory, of course. Quantum physics has this thing called Planck scale. So when you cut things into a smallest possible space,
10 to the minus 33 centimeter or something,
and then 10 to the minus 43 seconds.
Yes.
And beyond that, it loses meaning. So 0 plus 0 plus 0 is 0, meaning that nothing really. It's just an information. It's like a data structure, so to speak, that we are dealing with right now.
Or kind of like the shortest unit you can go. About the space and time.
Right.
That's it. For example, if you have a water, you could say that if you make a water half, then it's still water. Right? You make a half, it's still water. If you make a half, still water. And then ancient people argued whether that can go forever or not. If it's not, there is some smallest unit that they call atom. And now we know, of course, that's the case. It's H2O, molecules, and so on. You cannot call this as a water anymore.
Right.
Although you have like electrons and so on, but it's not water anymore. So this scale corresponds to that for space and time. If you cut the space half, it's still space. Half is still space. But in this Planck distance, that concept will stop making sense.
Right? So the reductionist approach stops right there.
And there's plenty of indication that would be the scale.
That would be the scale. So, and then what is that? This like piece of space, time space.
Exactly. So that's the thing current theoretical physicists are working on. We don't really know.
Informatics.
Yes, we use the language of quantum information to describe those things because they have to use some language, which should be based on the mathematics.
Right.
And usually, we have like differential geometry or many language we use, many mathematics we use. It seems like the information theory is the right language to describe what's happening there.
Shannon theory.
It's an extension of Shannon theory, called quantum information science.
Right.
It seems to be the right language, but it's not completely sure. By the way, if you don't know, the humans have not directly probed that Planck scale. We are still 15 order of magnitude away. But we are doing pretty well, by the way. If we have atom, and nuclei inside atom is 5 order of magnitude smaller than size of atom. For example, if the nucleus is like the size of dime, and then the electron is circulating like a kilometer away. So the nucleus is very small.
Right.
And we even understand nucleus made out of something called proton and neutron. And proton and neutrons made out of something called quarks. So we currently have 1 in 10,000 of a nuclei is the shortest scale we directly probe.
You can actually see it.
Yes. Not by light. Actually, the smashing things.
If you hit light, then it goes away.
Not necessarily even light. Like smashing 2 particles together, it's called accelerator. And then break it and reanalyze like what's going on at the short distance scale. But the Planck scale is still 15 orders of magnitude away from that. So
getting close, but still
it's closer than the old days. But so it's still theoretical. Exploration is a main tool, but we pretty much know that at the Planck scale is continuum of space. The idea of a continuum space, like a continuous water, will stop making sense.
Makes it stop.
But then what's really like the shortest kind of unit of space or shortest unit of time, we don't completely know.
We human beings or sentient beings or maybe bioorganisms, we use our sensory perceptions to gain access to those data structures. And that's how we sort of experience time, space-time, and the rest of everything else. Right. So I have a theory actually. So for the longest time, the second thermodynamics is promoting the idea of the entropy, meaning like time. The arrow of time is actually increase of entropy. I think the
statistical phenomenon.
I think time is about adding information, like accumulation of information. So even entropy is an addition rather than subtraction. It's actually adding information to the situation. So actually, the accumulation of time, information is the arrow of time. Is my, that's something.
Pretty much the right word because entropy is in some sense it's just a measure of the information. So entropy increases almost means, in some sense, accumulation of information, or the other sense. It's not completely one-to-one correspondence because if it's the highest entropy state means what? Highest entropy state is, for example, like you have, if you have a coffee and if you drop milk, and then you have some information, right? Milk shape and so on. But the highest entropy state is just cafe latte, right? I mean, it's just, and then there is no information. Everywhere is brown, right? So the highest entropy does not necessarily means highest information in that sense, but in the other sense, how many configuration corresponds to this brown cafe latte? How many configuration of molecules and so on corresponds to this coffee with the milk here? The number of configurations of molecules corresponding to this brown cafe latte is larger. So in that sense, I have a lot of information, but it's not information usable because it's just brown. Only one information. There is no shape or so on. If it's not the brown, if the milk is not yet completely, scrambled with the coffee. Then you have a lot of information, right? Even though you can write drawings on the coffee using milk.
Exactly.
Or you can have, but then if it's everything's scrambled up and then it's just brown, no information.
But that doesn't mean time stops right there. The time will continue to progress.
But if you define the time as an entropy, as
an entropy,
then it stops. So it's all definition. I mean, but microscopically, of course, still molecules is like scattering and so on. So in that sense, time is there at the microscope level. So the time, if we say time is this simple concept of time, you can define them many different ways. And in a simple situation like our own world and the usual situation, then many of the definitions agree. That's why we use any one of them as a definition of time. But in some different situations, depending on definition, of course, the concept, in fact, the probably time we introduce just for convenience to describe the system.
Right.
So because can you measure the time? Is a time 3? 4, it's a correlation, right? It's like we say like 4 seconds later.
Locality.
Yes, it's a correlation of events. Not the time itself as an object.
Right.
We just introduce the time as describing correlation of some events happening, and as a result, some other events happening.
Exactly.
And we introduce a concept called time.
Right.
For convenience.
Convenience, Yes.
And then what Einstein told us is that
locality.
Yes, locality in space and so on. What Einstein told us is that this is not always completely arbitrary. For example, if you just introduce in time, even though you could say that the time is just introduced by convenience, if you introduce this time, like a time slice equal time, in a way Newton did, it's inconsistent. So you have some rule to introduce this time, even though it's just like artificial concept introduced for describing system, but you have certain rule, and that rule was not the one Newton imagined in the end. So the Einstein corrected that, but still we now think that just the concept of time itself was some artificial concept introduced by human to describe certain correlation in the world.
Okay.
So that's the current state.
Sounds good.
But you can introduce in many different ways.
Okay.
Okay,
lastly, I'd like to ask you what you are currently working on. And some say that you're one of the closest guys to Nobel Prize.
No,
you never know.
I never know, but I wouldn't say that. But anyway, the prize being aside, I think not just me, the people in this field, especially theoretical physicists, caring, is our world is working quantum mechanically. Some theory called quantum mechanics is a basis of how world operates. And that we knew because the quantum mechanics was constructed 100 years ago. In fact, this year, I don't know when this is broadcast, but right now, this is 100th year of quantum mechanics. UNESCO really? Declared this is 100 years. That's the 2025, by the way.
Is it Schrödinger or Planck or
Heisenberg? Heisenberg first wrote down the equation. Of course, when it's constructed, it's a difficult question. Like many people added, Planck was done in 1900.
Right.
And Niels Bohr is 1910-ish. Einstein 1905. And then, but the Heisenberg first wrote down 1925 the equation, and Schrödinger's year after. So it's 26. By the way. So the 25, 26 is like 100 years. But we also have something called gravity, the phenomenon gravity. The gravity is now understood by Einstein very precisely by the theory called general relativity. But combining these two theories into a single theory is not easy. People tried, and you can effectively do it.
You're trying.
Yes. But and you can effectively combine it. That's no problem. For example, describing some daily phenomenon, not daily even, it's just a cosmological phenomenon, there is no problem. But in a very extreme situation, for example, like the center of the black hole or whatever crazy situation, you need the single theory which contains both phenomenon, quantum mechanical phenomenon and the gravitational phenomenon in a single theory. That theory we still don't have. We have a candidate called superstring theory or whatever, and we have a candidate, but those theories were kind of defined only approximately. So we don't have even fully defined the theory of something called quantum gravity, so combining quantum mechanics and gravity. So this is the one of the goals theoretical physicists are aiming, and we're making progress in the last 10 or 15 years. And our perception of what's at space and time changed. One of that is like information theory. That's relatively new. It's the last 20, 25 years thing.
Right.
So we are making progress. So it's not yet there. Because if you
what's your contribution to this?
Oh, okay. I think I've studied this theory, and there was something called the multiverse, and there was many universes. That itself is not something I came up, but there was some difficulty in this framework of multiverse. It explains something called dark energy of a universe. This multiverse is essentially unique theory human has to explain that already observed phenomenon. And this multiverse is something suggested by equation of quantum mechanics and gravity. And yet, multiverse has some small, difficulty of something associated with infinity. If you try to calculate certain quantity, you hit the infinity. And I propose a way to eliminate that infinity. That's one contribution. Of course, I'm doing some smaller stuff in here and there.
What does prediction mean in multiverse? Like when you try to predict something, do you think there's the prediction actually model kind of evaporates? It disappears when you say.
One thing is dark energy. Actually, kind of perhaps a post-prediction in a sense. Namely, we found something called dark energy in our universe. That is accelerating expansion of the universe. That's a very strange thing because gravity is universally attractive. So even if the universe is expanding, that was 100 years ago discovery, even if the universe is expanding, it should decelerate because everything is attraction. But current universe turned out to be accelerating. And the origin of that is the energy of the vacuum, which theorists call, for example, energy space-time itself has. For example, you get rid of the table, if you get rid of the chair, you get rid of even air molecules, and it still has energy. That can accelerate the expansion. That's what's kind of known. That's something probably what we discovered by accelerating universe. But this energy of the vacuum or energy of the space and average energy of the material called matter, right? Disk and galaxies and star is almost the same size right now. This is extremely strange thing, theoretically. It almost never happens. And the one way or only way we know to understand or to explain that fact is we have many different universes. It's the same thing like this Earth. Earth has a forest and lake and beautiful, extremely beautiful, because it's a finely tuned. Distance from sun is right, and the size of the Earth is right. If it's smaller, all the water molecules evaporate. So this is extremely fine-tuned. Some God may have, created this planet because usually you might think that planets should be much hotter or much cold and ice or liquid helium or crazy stuff. But somehow we live in here. It's very miraculous. But it's not miracle because we have a lot of different planets. Even within the galaxies, we have a lot of different planets. And actually, most of the planets are super hot or super cold or liquid helium and so on. And then only small portion has a right condition. And only on those places, the human or some intelligence life developed. So if they make an observation, they always discover it's a miraculous, crazy. Finely tuned, somehow some intelligent design or something, but it's not. Because you have a lot of different varieties, and you yourself will show up only in tiny place, very miraculous condition place. So if you make observation, you always see miraculously well-designed environment.
What does that have to do
So
with
same thing seems to be happening. In our universe, this energy of the space and energy of the material seems to be so close right now. That's theoretically almost impossible to imagine, but it's happening. We already checked. The one way is to understand is that you have a lot of different universes where this ratio is completely random and different. But people calculated, this is Steven Weinberg, Nobel Prize winner, calculated if this is not like our current thing, there is no galaxy, no star, nothing forms. So only in this miraculous place where two energy densities are close, intelligent life, or even just even the stars and so on, galaxies, let alone intelligent life, will show up. So only on those places complex structure shows up. And if you make observation, you will see this miraculous thing, crazy miraculous thing. We actually found that. And then after that fact, that's the only way we could understand. But then you have to accept a lot of different universe where like these properties of vacuum energy or property of particle species and so on are different. But then if you went back to the equation we wrote down in 80s called string theory, which is only candidate to unify quantum mechanics and gravity. And if you analyze that equation already contained a lot of different universes with a different vacuum energy and different particle content, so on. People rediscovered. People back then dismissed because our universe is fun. Okay, what's crazy? There's many universes. Forget about it. But because of that, we can understand observation fact, which was discovered in 1998, that our universe has a similar size of energy density of material and energy density of space. That crazy fact. You can understand by having multiple universe, which is already in the equation we wrote down.
In string theory.
So yeah, and then so that framework seems to be quite reasonable, and that's the only theory we currently have to understand dark energy, or namely energy of space.
Okay.
But still had some small. Not small. What I solved is big problem. Anyway, they had the problem with infinity. And the way to address that infinity is one of my proposal. Yes. So because you asked like, that's my work. Yeah. The multiverse itself is not. Okay. Was
it's something already proposed by somebody else. Okay. Professor, very nice. Thank you very much.
Thank you very much.
Thank you.
Great. Thank you.
Appreciate it.